Back to carbocations. So here we go. This is the material that we just covered in the last video. Imagine I have this tert-butyl bromide and I put it in water, probably heat it up, although I don't really have to. What's going to happen is that I'm going to break this bond with some of that heat energy. I can do that because both of these ions are relatively stable. Both the bromide, which we always have, and this tert-butyl cation. This is a carbocation. This carbocation we talked about can act as a weak Lewis acid, which is to say electron acceptor. This water can then act as a weak nucleophile and come in and make a bond to that carbocation. Okay, so again, it's a two-step reaction. First, I wait for that bond to break to give me a carbocation. And carbocations are now reactive enough to react with basically anything. Water is a weak nucleophile, but it's good enough because it has a lone pair. That lone pair then goes to make a bond with the carbocation. We get this intermediate, which is just the conjugate acid of this tert-butyl alcohol. That is what we would call the SN1 reaction. But that's not the only thing a carbocation can or will do. Just like water is a weak nucleophile, it's also a weak base. But it's good enough to take one of the protons next to that carbocation. So let's draw the arrows. The lone pair, those electrons go and grab that proton. These atoms, or these electrons that are holding these atoms together, those electrons are going to go here to make a new pi bond. So our product looks a lot like the E2 reactions that we talked about earlier. And again, I end up with H3O plus, and that is reversible. We'll actually start off our Organic 2 class by talking about this backwards reaction. Start with an alkene, add acid, get carbocation. But for now, we're going this way, right? Get carbocation from something like this bromide, leaving group leaves. Carbocation will either react to make a new bond and do an SN1 reaction, or will give away a proton to get to this elimination product, this alkene. We're going to call that E1, just like SN1, because it's unimolecular. The 1 means that the slow step involves one molecule, tert-butyl bromide. Back when we were talking about SN2 and E2, we talked about what might bias the system more toward the substitution product or the elimination product. This is a little bit different. The SN1 and the E reaction share the same rate-determining step. In both cases, I'm starting with this thing, and I'm trying to get this cation. Getting over this hill is the hard part of the reaction, right? Imagine mini golf. If you can hit a ball with enough energy to get over this hill, it's probably going to sit and go over pretty quickly, right? So the hard part is getting over this hill. So really, I'm going to see both the E1 and the SN1 products show up when I do this reaction, right? So I am going to see alcohol and alkene if that's possible. So because they share a rate-determining this step, we would pretty much expect them to happen together, again, in a reversible way. When we talked about the E2 reaction, we had lots of stereochemical questions, right? We had said, okay, let's draw the Newman projection. Let's think about getting the H and the leaving group anti to each other, all that kind of stuff. For the E1 reaction, it's actually a lot simpler. Because this is a reversible reaction, we're going to go back and forth. We know that we're going to get the most stable alkene as the major product, full stop. So what does that look like in practice? Here's an example. Here is a tertiary chloride. Here is the cation it can form. So draw on your own a couple different possible alkene products we could get from this, and then let's try to maybe gauge which one we would expect to see. So there's actually quite a few alkenes that we can imagine coming from here, right? We've got lots of hydrogens around the thing, and we could think about which of those we would expect to take. We've also got lots of cis and trans isomers. So how do we think about what the most stable of these is going to be? Here, we're really looking at conjugation. We want our new alkene to be conjugated to the benzene ring and not be separated from it. That's going to be a big, important stability thing. So of these are going to be the most likely formed. Probably aren't going to see much of those, especially not this one, right? Because that is not very substituted. And the more things I can put around the alkene, the better, right? There's only 1, 2 things there. That is a small number, 2 compared to 3. But what makes this better here is that not only is it tri-substituted, 1, 2, 3, but it's conjugated. And what's better among these two? Well, they're pretty close. I guess I probably want the one where the bigger groups are trans to each other, because here the bigger groups might bump into each other a little bit more. So my guess would be that this one would be formed the most. But you would probably see a lot of these products formed in some amount. Let's review. This is carbocation chemistry. Carbocations are involved as the intermediate for 2 reactions here, the SN1 and the E1 reaction. Starting from something with a leaving group, ending up with some substitution product, that's the SN1, and some alkene. Alkenes are elimination products. The rate law is just the rate constant times the concentration of tert-butyl bromide here. Does not depend on water concentration or the nucleophile concentration. In general, I'm almost always going to have very weak nucleophiles and very weak bases, which is to say the solvent is probably the base or the nucleophile, and that solvent is probably one of a pretty small set of really, really polar compounds. Water, methanol, ethanol, maybe acetic acid. The reason I need really polar solvents is because I need to make it easy for me to make this really polar intermediate, right? So polar solvents stabilize polar intermediates and also stabilize the transition state to the polar intermediate. So that's why I need polar solvents, because I have a polar intermediate. Stereochemistry isn't going to be as tricky as SN2 and E2, right? It's also not going to be as useful. For SN2 and E2, if you show me the stereochemistry of your starting material, I can tell you what the stereochemistry of your product is. It's going to be specific. Here, my stereochemistry is really not going to be specific, right? This thing is flat. I can add stuff from either end. Also, these reactions are reversible. They can go back and forth really readily. And so that's another reason why I'm basically going to see scrambling, and I'm going to see the more stable product as the major product, right? In this case, if I'm making some achiral flat thing and I could get 2 enantiomers, I'm going to get a 50-50 mixture of configurations at that center. Carbocations are also tricky because they can rearrange to give more stable carbocations. And this is that hydride shift and methyl shift stuff that we talked about. Again, I'm not going to ask you to really arrow out lots of complicated shifts, but I do want you to recognize that that is a problem that we could face when we are trying to do SN1 and E1 reactions.